So last time we talked about dipoles as a simple example of superposition, but also because dipoles are super important in nature, as we will continue to explore today. And just by applying the superposition principle, we found that for a dipole on the dipole axis, which is the axis that goes through both charges, we got an expression for the electric field that was 1 over 4 pi epsilon 0 2 qs over r cubed approximately, as long as we were significantly further away than the distance from the dipole was significantly more than the separation of the dipole. So the charges on the dipole are a plus q and a minus q. And that's not a vector expression, that's a magnitude, because depending on the orientation of the dipole, the field here could be pointing this way or that way, and so you have to figure out, just from looking at the situation, which way it's going. We also got an expression for the dipole field on an axis perpendicular to the axis of the dipole at some distance r. And we found that E on the perpendicular axis was also went like 1 over r cubed. But it was actually a factor of 2 smaller in magnitude. And that was due to the fact that although the magnitude of the contribution of each charge is the same at this distance, a lot of that is actually in the y direction, and that part cancels out. So what's left is... And we also defined a quantity dipole moment with the unfortunate symbol of p. It's the product of the amount of charge on one end of the dipole, this is a positive number, times the distance between these charges. And it's kind of a measure of the strength of the dipole, because you can see that each of these fields, the magnitude of the field is dependent on this quantity. If you increase either q or s, the field is going to get bigger. So that the bigger the dipole moment of a dipole, the bigger the separation. Dipole moment is something that you can measure sometimes, whereas you don't necessarily know exactly how much charge is separated by how much. So it's a... These are concepts that we're going to use a lot today. Now, a couple things came up in recitation that I just want to comment on. And the real issue is, there are 2 issues. One is, what's fundamental? What do you really need to know? What do you need to memorize? And what is something that we've just derived that we'll give you an equation for? Right now, these are quantities we've derived. You do not need to memorize these equations. It's helpful to know that the field of a dipole falls off like 1 over r cubed, which you'll sort of get from working with dipoles, but you do not need to memorize. what do you really need to know? Some of you were looking for equations about forces between dipoles and point charges. That is actually not where we want your head to be. So what's really fundamental is that if you know the electric field at some location in space due to some charges in the surrounding, which could be one or more dipoles, then you can predict the force on any charge that you put at that location just by multiplying it by that electric field. Okay, and this is a signed number, it's plus or minus. So this is our system. That's the electric field due to things in the surroundings, or sometimes this is called the applied field. This is something that you do need to memorize and you really need to know. So what's the other thing that's fundamental? Well, we're going to be spending a lot of time calculating the electric field due to various kinds of charge distributions that we may encounter in the world. And we're always going to start with the electric field of a point charge and then find a way to set up the fields of point charges to get these electric fields. And so this is the electric field of a point charge, 1 over 4 pi epsilon 0, the charge of the point charge over the magnitude of r squared, r hat. And by memorized, it also means know exactly what these symbols in the expression mean. So what is Q? What is the vector r? Because in order to get either the magnitude of r or r hat, you need to know what the vector r is. You need to know that it goes from the thing that's making the field, the source, to the observation location, the place where we're measuring the field. So all that surrounding knowledge about an equation, you need to also know. And we'll keep coming back to this again and again and again, because a lot of what we're going to be doing is figuring out what a field is somewhere and then predicting what effect it'll have on a charge if we put a charge there. So comments about that? Questions? No. Okay. The second thing is, just as last semester when you were calculating gravitational forces, when you do calculations involving equations of this kind, where there's a bunch of steps, first you have to calculate r, then you've got the magnitude of r or r hat, you've got to square this, you've got to divide. You have to keep, as just a functional matter, you've got to keep a lot of significant figures in your intermediate results. Don't round, because what the computer is doing when you're doing homework is it's doing what would happen if you were doing. It's keeping all those intermediate significant figures as it does the calculations. And so when you get to the end, if you've rounded to 3 significant figures with the magnitude of r, and then you've rounded the components of r hat and whatnot, you may end up being more than whatever it is, 1% away from the calculation. So even if you report, when you type your answer, you don't need to report 10 figures, but when you do those calculations, keep those significant figures, which happens automatically if you're doing them in GlowScript, which is another reason to use VPython for your calculations. But okay? All right. So what's the direction of the electric field at the location of the point charge due to the dipole? So if you're not sure, talk to your neighbor. If you are sure, talk to your neighbor just to see if your neighbor's sure of something else. Okay, so what's the direction? Yes, the direction is indeed, the answer is 1. The direction is indeed up. And that's because although both of these charges contribute to the net electric field at this location, which is the observation location, right? This one's closer, and so it makes a bigger contribution, so the sum ends up being small, but in that direction. Okay. What's the direction of the electric force on this point charge then due to the dipole? Yep, the force is also up because since the field was up and the charge is positive, the force it experiences is in the direction of the net field made by objects in the surroundings. Okay. All right. So with that review, we're ready to apply some of these ideas in talking about the interaction of charges with ordinary matter. Now this chapter is a little different from what we've been doing in that there aren't an awful lot of equations, sort of a lot of concepts, and a big emphasis on reasoning. Reasoning that may or may not be supported by equations, but so thinking qualitatively about what's going to be happening. So the basic, and there's some vocabulary, which we'll try to note. So the basic idea here, so here's some vocabulary, some definitions. We all know that matter is made of charged particles, protons, electrons. The net charge of an object is what it sounds like. So net always means the sum of everything, right? So we just add up all the positive charges and all the negative charges, and we get the net charge of an object. For example, carbon atom has how many protons? 6. How many electrons? What's the net charge of a neutral carbon atom? 0. So neutral means net charge is 0. And most things are neutral. They're made up of atoms that have... So what is the net charge of a hydrogen ion? Well, it's +1, but what's the charge in SI units? Yeah, it's +E, isn't it? So a carbon atom, 0, H plus, it has 1 more proton than electron, so the net charge is +E, which is 1.6 times 10 to the minus 19 coulombs. What's the net charge of a chloride ion? Yeah, so minus E, a minus 1.6 times 10 to the minus 19 coulombs. If something is neutral, it's neutral. If it's not neutral, we say it is charged. That's if its net charge is not 0, we say charged. Okay, so it turns out there's a new fundamental principle that we haven't talked about, hiding in all of this. And the fundamental principle is actually conservation of charge. And like the other principles that we've expressed as conservation laws, it says that something can't change. In this case, what this says is that the net charge of a system and its surroundings can't change no matter what kind of processes go on. So So let's think about some processes and see what this does for us. So suppose we have a water molecule which dissociates and it goes to an H plus and an OH minus. Now all of a sudden we've got some objects with non-zero charges here, where before this was neutral. So does that violate conservation of charge? No, because these charges still add up to zero, don't they? Okay, so net charge didn't change. How about one of our favorite processes? We have an electron and a positron, an anti-electron. They come together. All their rest energy is converted to kinetic energy of 2 photons. So we've got 2 gamma rays, 2 high energy photons going out. Now a photon is a particle of light, and it does not have a charge. Didn't we just violate conservation of charge here? Yeah, the net charge is still 0. So we had a net charge of 0 here. We have a net charge. So any process, if we consider the charge of the system and the surroundings, the net charge of surroundings doesn't change. Okay. There's also a way of classifying matter into 2 categories of objects, and we're talking about macroscopic matter here, things that are made of lots of atoms. And there are some things we call conductors and other things we call insulators. And what this means functionally is conductors contain mobile charged particles, and insulators do not have any mobile charged Now what's a mobile charged particle? Well, it means a charge that's really free to move kind of a long distance. So for example, if we had a beaker, the solution of salt water, so we've got lots of water molecules, but we've also got some sodium ions and some chloride ions. So those ions, or solvated ions, or whatever they are, they're still charged. They're free to move around this entire beaker, right? They can move macroscopic distances, much, much farther than an atomic diameter. They can move centimeters or meters if it's a giant beaker, right? So this thing has mobile charged particles. And it counts as a conductor. On the other hand, if we had a crystal of salt, where we've got an array of sodium ions and chloride ions. Whatever. These things are bonded together by chemical bonds, and they're not free to move around in the crystal, and therefore there aren't any mobile charges. Okay, so it depends on the form of matter. Now, where do these names come from? Well, clearly this is, so a lot of names when we're talking about what's called electrostatics, charges that experimenting with charged objects, come from talking about what happens in an electric circuit. And so what a conductor really refers to is, can an electric current pass through this thing? Can it conduct electric current? An insulator insulates against an electric current going through it, and therefore it doesn't conduct an electric current. So how do you decide if something's a conductor or an insulator? You probably actually have a fairly good intuitive idea of what's a conductor and an insulator. There are a few surprises. But, so here's our light bulb driven by batteries. Presumably these wires are conductors because we see that probably an electric current is flowing through here, that's what's making this light bulb light up. What's an electric current? It's just a flow of charged particles. That's all it is. And we'll actually, so we are insulators to first order by just putting one in the circuit and seeing what happens. So here's a piece of aluminum foil. Do you think it's a conductor or an insulator? Probably a conductor. Metals tend to be conductors, don't they? So if I clip my clip leads to the piece of aluminum foil, you're correct. Electric current can flow through it. So therefore a metal like aluminum is a conductor. And other metals are conductors too. If I put a penny in there instead of, what's a penny made of? Yeah, whoever said copper and zinc is right. They used to be made of solid copper, but they aren't anymore. It's mostly zinc, and there's just a thin layer of copper. And an amusing thing to do if you have a chemistry lab is to make a little hole in the copper and digest away the zinc with an acid, and you're left with a very thin copper foil. But okay, so either copper or zinc, whatever we've got. It's probably also illegal because you're defacing currency, right? But it's still amusing. Okay, so what about a piece of invisible tape? Think it's a conductor or an insulator? I think it's an insulator. It's made of plastic, right? Plastic's got these big long chains of carbon, hydrogen molecules, right? So if I can do this without permanently sticking myself to the desk, and I think about 2/3 of you experimented with invisible tape yesterday, right, in lab. The remainder will this evening.
Yeah, good luck.
And you're correct, we do not get a lit light bulb, so tape looks like there are no mobile. There are plenty of charged particles in the tape, but they can't move very far. Not enough to sustain an electric current. So that's kind of the operational definition of conductor and insulator. And of course there's some nuances, because if I put my finger in the circuit, I'm not a conductor. However, if I were hit by lightning, I would be a conductor. So it depends to some extent on the energy of these situations. Yeah, and air is also an insulator. So air is a pretty good insulator, but we can get sparks in air, so yeah.
In the conducting properties of
So the question is, can the conducting properties of a material change if it's charged static? And it's a good question, because you've seen things come out of the dryer very staticky and clinging to things, and we're going to be talking more about charging things today. One of the properties of an insulator is that when an insulator becomes charged, you rub a balloon on your sweater or something, the charge doesn't move because there's no way for it to move, so it stays in patches on the surface of the object. It's static, right? It's static means doesn't move, doesn't it? So, so even if it's charged, that isn't necessarily going to make it a good conductor because those charges can't move. They're stuck. So, okay. So how do objects become charged? And we've seen that, I mean, you've just raised the issue that things that we believe are insulators, like balloons, or as you have seen or will see, a piece of invisible tape, can become charged. And so how does that work? Now, becoming charged means that the net charge is no longer zero, so either charges have been added or taken away. And the question is, what could be added or taken away? So most of you are familiar with this approach to charging a piece of invisible tape, where what I'm doing is I'm putting the piece of invisible tape down on another piece of invisible tape and smoothing it down, and then I'm going to pull it off. And now I assert that it has a non-zero charge, which is fairly clear because it's attracted to lots of things. But let's say that this tape is charged negative. I think actually this tape is probably charged positive because it's Scotch tape. Let's say it's charged positive. The charge, this is all really very complicated. There's a lot of surface chemistry that goes into this. And so the charge you get on a piece of tape actually depends on the brand of the tape. And so you have to have something that you know the charge of to test it. But, okay, so it's attracted to my hand, it's attracted to the desk, it's attracted to Andrew's laptop. Does that mean all those things are negative if the tape is positive? No. And that's interesting. It seems to be attracted to neutral objects. Hendrik.
You could quickly make something have a negative charge, like a pencil or something.
And, well, one way to do this is to make something else with a negative charge. The only way you can really get repulsion is to make two things with the same charge. So here's, okay, you're charged. I'm going to try to put it there. Okay, and with a little luck, this hasn't become, ah! Yeah, I know. You're laughing because you had to deal with that yesterday, right? Okay, but it is actually repelling. You could see that it's
just a really sturdy piece of tape.
Yeah, so it's definitely repelling. Okay, so repulsion is a clear test for charge. We know these things are both charged and they have the same charge because they repel each other. So that's, and you have much to look forward to if you have lab this evening. But the question we're going to explore today is, why is a charged tape attracted to a neutral object? Because the electric field of a neutral object should be zero, because its charge is zero, and therefore its interaction with a charged object the net force should be 0. So what's going on? Caden.
That neutral objects still have positive and negative charges, and when you put, let's say you put the positive tape towards it, it pushes those positive charges away and brings the negative ones forward, making it attractive to it.
Okay, so Caden is saying a neutral object still has positive and negative charges inside it, and so when you bring a charged tape near a neutral object, you're actually say it's a negatively charged tape, you're shifting negative charges away and pulling positive charges toward it. In other words, you were totally messing with the structure of this neutral object just by bringing a piece of charged invisible tape near it.
So powerful.
Well, it's an interesting hypothesis and it's a very good one. So if we think of a model of a neutral atom here, diameter, the radius of a neutral atom is on the order of, or the 10 to the minus 10th meters. Depends on the atom. But what we've got is all the positive charges are in the nucleus, whose diameter is 10 to the negative 15th meters. So it really shouldn't even show up on this picture, but if you're close enough, you could see a little red dot here indicating that that's at least the location of the nucleus, although it's 10 to the 5th smaller, so we shouldn't be able to see it at all. And then this nucleus is a sort of fuzzy cloud of negative charge. Even if there's only one electron, even if it's a hydrogen atom, that electron, you can think of it as moving around the nucleus, never staying in one place. The result being that there's a spherically symmetric, what's called electron cloud of negative charge surrounding this. We have a tiny positive charge in the middle, and then this sort of fuzzy ball of negative charge surrounding it in a neutral atom. And the net charge is 0. However, if we bring, say, a positively charged object near this atom, then indeed the positively charged object is going to make an electric field at the location of the atom. And that does exert a force on both the electrons and the protons in the nucleus. And what it's going to do is it's going to make the nucleus move. The nucleus is quite massive compared to the electron, right? We've got a factor of 1,000 in mass here. So the nucleus might move a little this way, but the electron cloud definitely is going to distort and shift this way toward this positive charge. Now, why doesn't the electron just go to the positive charge? It's still attracted to the nucleus, isn't it? And that's a lot closer. So we've now got a distorted atom with sort of more positive here and more negative over here. What have we made? We've made a dipole. We turned the atom into a dipole just by bringing this charged tape near it. So we say that we have actually, let's recycle this board for this. We say that we have polarized the atom, meaning we have turned it into a dipole. And what did it? Well, it was the effect of this external charge. So we say that you'll hear people say, it's probably in the book, the applied field polarized the atom. What that means is the field of something in the surroundings applied to this polarized. So it's the effect of the applied field that did that. And we also could say the atom is now polarized. Yes, Flavio?
So the field on the proton, the applied field.
In this case, the field due to the proton. I wouldn't say on, because that sort of implies a location. So I'd say the field due to the proton at the location of the atom is the applied field. Yes?
How does this work with, atoms with only one electron? Because we kind of see that cloud, but with one electron, does it just kind of have a preference for being in one location at that point?
Okay, so Charles is asking a quantum mechanical question. He says, if the atom only has one electron, how can it be a cloud? And this is one of the cool things about microscopic systems, in that when you get down to the microscopic level, things that we think of as a particle, like a proton or an electron, have particle-like characteristics, but they also have wave-like characteristics, and they don't exactly have one location. What you have in a situation like this, so it's partly a particle and partly a wave, and what you have in a situation like this is really just a probability or a probability density of finding the electron here, here, here. The probability of finding it out here in a hydrogen atom in its 1s state is smaller. There's some probability of finding it out here, but it's smaller. There's a very small probability of finding it here. There's some probability of finding it inside the nucleus. That's weird. And so even a hydrogen atom basically has, for all experimental purposes for interacting with it, has this cloud, spherically symmetric cloud of negative charge surrounding the nucleus. And it's pretty neat that microscopic particles systems have these properties, but then when we take lots of them and add them all up together, we get the behavior we see here, where baseballs don't act like waves, and you always know where a baseball is. And so, did you have a question?
So the electron on hydrogen, because it has that spherical shape,
Yeah.
could you say that maybe that's just like its trajectory is moving so fast around the atom that it just hits all those points?
So one way of thinking about it is indeed that you could think about the electron just moving fairly rapidly all around the atom and being in all of these places, in which case this representation is kind of like a whole bunch of snapshots superimposed. So every dot is, well, we saw it there at that point, there at that point, there at that point. But the only thing we can predict is just kind of a probability cloud, a probability density and in general, it's probable that it'll be a certain set of distances and not farther, and yeah. So, Robert?
So does polarization always have to happen with like s electron orbitals?
No, the whole thing can, no, it's not just s orbitals, it's all the electrons are subject to external fields. Now, the electrons that are farther from the nucleus are feeling the effects of the nucleus less, so they may be easier to polarize.
Yeah,
So the inner electrons are going to be harder to shift, and the outer ones are going to be easier.
no, it's because I'm asking the question because s orbitals are always like kind of spherical, and like the orbitals are bell-shaped. And then
But what you see, yes, and so I think it's a mistake to think about, atoms having. Okay, there are orbitals that have different shapes from spherical shapes, but in fact, this atom could be oriented in any. It's probably rotating. It could be in any direction, and actually, there's some orbitals too, and so we have pz coming in and out, and then there's some s stuff, and the result is it ends up being spherical. Now, once you start bringing a different atom toward it and things combine, then things get more complicated. But just an isolated atom, it's. Jonathan?
So is polarization always attraction?
Ah, so that's a very good question. Is polarization always attraction? So what if this charge were negative? What would happen?
You shift the cloud. Yeah.
You shift the cloud the other way, wouldn't you? And so, oh, there's another term. There's another term here. This atom is called an induced dipole, meaning you induced it. You persuaded it to become a dipole by bringing a charge near it. And it's different from HCl, which is a permanent dipole, because if we took this charge away, it would go back to being completely spherically symmetric, right? So we're going to need to draw diagrams indicating that atoms have polarized. And it's impractical to draw something like this. So what we're going to do schematically is we're going to draw it kind of like this, where we say we've distorted it with positive charge over here and negative charge over here, because that's something we actually can draw and communicate with each other about what this means. And so what does this mean? This is a atom or molecule. So the envelope means that it's constrained, it can't move farther. And this indicates that there are inside of it positive and negative charges which are slightly separated. Now, this is a big exaggeration of what's really going on. I mean, I'm not even sure I can draw it. You know, probably what we have is the nucleus is here, and what you'd call the center of the electron cloud is here, or something like that. But we're going to exaggerate it in our diagrams just for the sake of communicating with each other about what's going on. And not surprisingly, if we apply a larger field, like we had an alpha particle there, and still, instead of a single proton, bigger field would polarize it even more. And it turns out that this polarization is up to a point where exciting things happen. So for quite a while, really, this polarization is pretty much linearly proportional to the magnitude of the applied field, so that so larger gives a larger what? Well, a larger dipole moment. Right? So, in fact, remember that we have dipole moment is the product of the amount of charge times the separation. We can actually, which is P is a proportionality constant alpha times the magnitude of the applied field. This is called the polarizability of the atom. And this is a small number, so it's on the order of 1 times 10 to the minus 40th. And let's see, the units of this should be coulomb meters. And this is newtons per coulomb. So it should be coulomb meters per Newton per coulomb. Yeah.
So because I know that based off of like that dipole moment or how far F is pulled apart, that affects the dipole moment, but even if it's like barely pulled apart at all, would it just have the same field of the dipole because it doesn't matter as long as there is at least a little bit S, I think.
So the question is, obviously, you know, it's going to take a big field to stretch an atom very much, to polarize it very much. But is a polarized atom still a dipole like the ones we talked about last time? Is it still have a positive and a negative charge and make a dipole field? And the answer is yep. Yep, it does. So let's actually try to calculate something here about how that would work. So let's let's say that the polarizability of a particular atom is 10 to the minus 40th coulomb meters, sorry, per Newton per coulomb. And let's say we apply a field, the magnitude is 3 times 10 to the 6th newtons per coulomb. Now that's an interesting number. It turns out empirically, air is an insulator until you apply a field this big or larger, at which point air ionizes and actually becomes a conductor. So this must happen in sparks and lightning and things like that. So let's say the biggest field that we can practically, if we assume that, well, let's calculate the dipole moment we'd get for this. So we'd get the dipole moment of this atom would be 1 times 10 to the minus 40th coulomb meter newtons per coulomb times 3 times 10 to the 6th newtons per coulomb. And so we get 3 times 10 to the negative 34th coulomb meters. If we assume that it's 1e that's shifting, we could calculate a separation. So S would be P over Q. So assume so that's going to be 3 times 10 to the minus 34 coulomb meters divided by 1.6 times 10 to the minus 19 coulombs. So that's roughly 2 times 10 to the negative, what's 34 minus 19? 15? 2 times 10 to the minus 15 meters, roughly twice the diameter of the nucleus, so a tiny shift. But will it still make a dipole field? Yeah. So in fact, if we consider on the axis, we have E of the induced dipole is going to be 1 over 4 pi epsilon 0. Just use the dipole moment here. 3 times 10 to the minus 34 coulomb meters divided by, how far away do we want to be? 3 times 10 to the minus 10th meters, not very far away at all, which gives us, that's going to be a minus 24, 9 times 10 to the 9th, times 1 times 10 to the minus 24, 10 to the 9th, 24, 15. So 9 times 10 to the minus 15th newtons per coulomb. Not real big, but it's not 0. Did I do that right?
I don't know.
This is 9 times 10 to the 9th. Oh, cubed. That's the problem. There we go. Okay. So 9 times 10 to the 9th. Okay, so we have 9 times 10 to the 9th. 3 times 9 to the minus 34. We have 9 times 10 to the minus 30th. So we have 3 times, we have a minus 4 and a plus 9, 10 to the 5th newtons per coulomb. That sounds better.
I think the 9 times 3 upstairs counts to the 27 downstairs.
1. Yeah, you're right. Yep, right. So we got, so if you're 3 atomic diameters away, it's making a big field. So not negligible. Falls off like 1 over distance cubed. Yes, Charlie.
Where did the R cubed value come from?
I made it up. I said we're going to be 3 times 10 to the minus meters away. So 3. You know, I mean, we could pick a value. We had to pick a value to get the. Yeah. Other questions? Yeah, Charles.
You mentioned that air becomes a conductor at a certain applied field. So when I like touch a doorknob or something, it's stacking applies. What dictates, that spark is allowed to travel?
Okay, so this is a great question. It's a question about sparks, and Charles said if it's cold out and he shuffles across the room and touches a doorknob and he gets a spark, what determines how far the spark can go, how big the field is. This is an awesome question, and it's such a great question that I'm actually going to defer it, because when we get to, we're going to talk about sparks in air, but there's some other stuff that we want to do first that's going to make it a little bit more informative when we do it. So stay tuned. It's really an excellent question. So given this, what would happen to a point charge here? Well, it would affect the dipole by, it would be attracted to it. In fact, there's something kind of amusing about point charges, which is kind of goes like this. Suppose we have what do I want to do? Yes. Suppose we have a positive charge and it polarizes an atom and turns into a dipole, and they're a distance d away. How does the force, let's say the force positive charge due to the dipole, how does it depend on the distance? It's pretty interesting because we have to step through this. So the first thing we do is we have to calculate the dipole moment of the new dipole, and to do that we have to get the electric field of the point charge. So we say the dipole moment is alpha times E of the point charge, which is alpha times 1 over 4 pi epsilon 0 Q of the point charge d squared. So that's, we've now got the dipole moment of the dipole. The dipole makes a field here in this direction. So the dipole field is now 1 over 4 pi epsilon 0, the 2 times the dipole moment given our orientation over d cubed. But that's equal to 1 over 4 pi epsilon 0, 2 times this whole thing, alpha 1 over 4 pi epsilon 0, q of the point over d squared. Yes, I know. We have a quiz. So the dipole field, which does go like 1 over distance cubed, suddenly picked up another, so that's just P, and now we have 1 over d cubed. So all of a sudden, the field of the dipole is, the induced dipole is actually going like 1 over d to the 5th between this. So the force on the point, which is QE dipole, is now going to be proportional to 1 over d to the 5th. And I think you may have seen this with your invisible tapes, because what we're getting is not much, not much, not much, not much, not much, not much, bang. Okay, so it's a really strong distance dependence in this force. Now, somebody asked a question about, was it always attraction to a dipole? Jonathan, I think. And so, in this case, you're going to see that a positive charge polarizes an atom or molecule like this. And in fact, the force will be attractive, right? Because the field of the dipole is pointing that way, and it's charge. And through reciprocity, that's the positive charge will attract the dipole with the same force, right? Equal and opposite. So what if the charge is negative? So how does the molecule polarize in this case? Yeah. So it's 4, isn't it? Polarizes that way. And that's going to be negative, isn't it? So is it possible to polarize something in such a way that it'll repel? No. So an induced dipole is always going to be attracted to the charge that makes the dipole, right? All right. Well, you asked a lot of good questions. And we didn't get quite as far as I'd hoped, but good enough. Other questions or comments?